Hey everyone, how's it going? It's Kestova here, back with another problem for the day. And this one actually came from another viewer request, so I'm pretty pumped that you guys are starting to like and comment on the videos that I've provided so far. This one comes from, and I might butcher the name, but Nabeen Dahal. And he actually sent me a request for a steel column design. So, Nabeen, that's what we're going to be doing today. And what I've set up is a 15-foot tall column that is pinned at both the top and bottom. And actually, this column is going to be a steel HSS 8x4 by 1/8 inch thick member. So an HSS member, for those who don't know, just in case, is kind of this is a box member. And in our case, it is going to be a rectangular box section. So the 8x4 denotes what the dimensioning is. So 8 inches tall by 4 inches wide. And then the thickness is going to be 1/8 of an inch. So I have not actually supplied a load on this column. Today we're going to compute and determine the axial compressive strength of the HSS with respect to both principal axes. Because we have two different cases here. We have bending about or compression about the x-axis, so this way, and then we have compression about the y-axis, so that way. And because its geometry is different in both directions, or in both axes, we need to figure out if that's going to affect our strength. So let's get into it. As always for this, since we're working with steel, gonna need your steel manual. AISC steel manual. I'm gonna be again working with the 14th edition. The 15th edition is out. It's been out for a little while now, but everything should be just about the same. So you should be able to follow along pretty easily with that one if you have it, so don't fear. All right, so what we want to do first is compute the flexural buckling strength. So what I do is actually, if you go to chapter E in your design manual, that's the design of members for compression, and that's what we're doing. So we'll flip that to the next page, and this gives us our table, and basically it helps you break down, well, what does your section of your column look like? And we have this one. We have a rectangular HSS member, and what it does is it gives you a little cheat sheet and tells you, well, what's going to be the limit states. And the limit state is what's going to be the effect that happens that controls the strength of the column. And that is based on the geometry of your column and the effects that happen. And that's been found through testing over years and years in laboratories to see what happens when you have these different types of geometries under different type of loading configurations. But we won't get into that. They've done all that for years and have tabulated it and have found the results. So you have two sections here. You have without slender elements and with slender elements. Well, we're going to jump back to that. We will need to figure out and check to see if our section is slender. But first, let's just assume it's not slender. So without slender elements, because if you look, for the limit states in both cases, without slender elements, you just have to look up flexural buckling. And with slender elements, you have two limit states. You have flexural buckling and you have local buckling, so FB and LB. So you have FB in both cases regardless. So let's find FB first, and then it doesn't really matter if it's slender or not, because it's required in both. So FB is what we're going to find first. And what that does nicely is it tells you what section it's in. So FB, section E3 within chapter E. Well, this is chapter E. We'll go to E3, and here we are. And there's the title, Flexural Buckling of Members Without Slender Elements. And this runs down, and it gives you all of your equations that are required. So that's where all of this is located. I'm going to jump back to the page that I have, but that's where all of my equations are coming from. So first we need to start off with KL over R. And actually, sorry, we're going to flip back. That's talking about the effective length section, E2. So you need your K, which is your effective length factor, and you need your L, which is your lateral unbraced length of the member, and then R is your radius of gyration. And actually, if we go to another little tabbed section that I have that I'm always going to is Appendix 7 for all of you future ASCE or AISC steel manual tips and tricks that you've seen in my last video. This would be another section of mine. And this gives you all the different, or a lot of different configurations of what a column and how it's connected and how it's braced. So it's pretty straightforward in this example for us. We are just pin to pin, top and bottom, and that means our theoretical K value is 1.0. And what's nice and what we use in typical engineering in the professional world is we use the recommended design value when ideal conditions are approximated. So it throws a little factor of safety on there. As you can see with all these, it's bumped up slightly. And what that does is gives you a slightly conservative number when you're designing your buildings, just in case if everything isn't according to plan. And it also, there's other factors that are taken into account, but it also, I like to think, takes into account if that beam isn't perfectly set or plumb when it's constructed and you get some accidental eccentricities in there. This helps account for that so that your structure is still safe. But for us today, it's easy. It's section or option D, pinned. So our K is 1.0. So KL over R, we have our K is 1.0. L, if we go over, is 15 feet. That's top to bottom of our column. So 15 feet, we're going to convert that to inches. So we're going to multiply by 12. And then R, and we want our least R in this case. And what we do is we are going to flip, you're killing me here. Hang on one second. Throw a sticky note in here. This is why, as you can see, we have everything tabbed up the way that I do. Okay. So we need to go back to our section properties. And let's see how quickly I can do it on the spot. Usually I have it tabbed up for you guys. 8 by 4 by 8. And this is in our table 1-11 of all our section properties. And radius of gyration is there. And so what we're going to need to do is check for both the X and Y direction because it's different. So for X, we're going to go down to 8 by 4 by 1/8 is 2.92 for RX. And for RY, it's 1.71. So we're going to use R 1.71. That's the least. Okay, so now we have everything we need. KL over R comes out to equaling 105.3, which is less than 200. You always want to keep it under 200, and actually that's noted right here in the user's note. It says preferably, but I've never seen an instant where we've allowed something to be to exceed 200. So that's a first little check, and that's okay. So we can move on. Next, we need to check that KL over R is less than or equal to this equation here. And again, that's in section E3 for chapter E. And we find that so E is just 29 times 10 to the 6 PSI, and FY is 46 KSI for rectangular members. So we convert that to PSI. You want to watch your units here. You want to make sure they're both equal. You can use KSI for both or PSI for both, doesn't matter, as long as they're the same. That comes out to be equaling 118. Now, since KL over R equals 105 and is less than 118, we get to use equation E3-2. We'll come back to the book, and equation numbers are marked over here. So see, when this is less than, we get to use F critical, that's what we're trying to find, FCR, equals this equation. But within the equation, there's also FE. We don't know FE. If we scoot to the bottom, FE is this equation right here. So we find FE first before we can find FCR. I know it's a little bit of a process, but we'll get through it. So here's our equation. Plug everything in. We have all of our knowns. And make sure if you're using PSI, you divide by 1,000 at the end. If you're using KSI, it'll just come out as KSI. So that's why I have that there. That equals 25.8 KSI. That's FE. And then FCR is now this equation. And we have everything, so we can plug everything in. And that gets us FCR is 21.82 KSI. And your compressive strength for flexural buckling is this equation here. Phi PN, I'm assuming LRFD. Phi PN equals Phi FCR times AG, area gross of the member. That's just Phi for compression is 0.9. So 0.9 times 21.82, that's our FCR, times AG. You can pull that from the material properties. If I can flip to it. Let's see. So you see area in inches squared, 2.7. Right. Oh, I don't even see my. Right there. Okay. We're having technical difficulties here. Hang on. I didn't mark everything accordingly. Okay. So we have everything. Plug all that in. It gets us 53 kips. Remember, watch your units, KSI and inches squared. So the kips per inch squared times number inches squared just gives you kips. 53 kips. That's your flexural buckling strength, and that's factored for LRFD. So that's the first part. So that's great. Second part, though, we need to confirm that whether our member is slender or not. So is the member slender? And what we're going to do is we need to take B over T. We need to find B over T, and we need to find H over T. And they're the same thing. They're just with respect to both principal axes. Because we said we wanted to check both principal axes for the strength. So one of them is 31.5 and the other one is 66. And you want to use the larger in this case for what's coming next. You can do this by hand, but again, if you go to the properties table, in table 11.1, they actually have right here, B over T and H over T. So just pull them right from there. Makes your life a lot easier. And what you need to do next, sorry about the camera working, I'm moving a lot. You need to go to your table B4.1, A and B. This is your compact limits. And in case you want a page number, there it is. And you have two tables here. You have width to thickness ratios, compression elements, that's what we have. Members subject to axial compression, that's what we're looking at. The other table is members subject to flexure. So it's compression elements subject to flexure. So we don't have that in this case. We're looking for a compressive strength. So we just want this table. And if you go down all of these, you are going to run into option 6, which is going to be an HSS. You can tell by the shape. And so you need to first find B over T for both directions. And that we've done. So B over T and H over T. And again, those are both in the properties section. Right there, B over T, H over T. And you need to compare them to your lambda R. And for our case, which is 1.4 square root E over Fy. We solve for that. Gets you 35.15, which is less than, and you want to use the larger value, so less than H over T, which is 66. So that means we have a slender element. All right, so we have to go find our local buckling capacity. So, since h over t is greater than, like I said, the larger dimension element is slender, and the local buckling strengths must be computed. Now, because the cross-sectional element, BT, equaled 31.5, and the other one equaled 66, 31.5 is less than your lambda r, which is this. So that is a stiffened element, and that'll come in handy because now we need to find Q. And what Q is, if we go back to our compression section, let's see, where do I want to go here? Back here to our cheat table, again, 16.132. Now we have slender elements. So now we need to go to chapter E7, because chapter E3 was flexural buckling, but now we need LB, which is local buckling, and that's in chapter E7. So we flip to E7, and we come up to members with slender elements. And what this all breaks down into is needing to find Q, and we know that Q equals QSQA, and then it gives you all of the different equations to find your QS and QA. Now we need to go to 16.143 because we want for flanges of square and rectangular slender element sections of uniform thickness, where BT is greater than 1.4 EF. So we want this. Now, we need to find Q, and Q equals QA, QS. We know that QS equals 1.0 because we have stiffened elements in the opposite direction. So if both your numbers for B over T in both directions were greater than 1.4 E over Fy, then we would need to find QA and QS. If both were less than this number, then we wouldn't have a slender element, which means that both QA and QS would both equal 1, which means that Q would equal 1 and there'd be no reduction. And it would equal, your local buckling would equal the same strength as your flexural buckling. And that's why we don't need to find it if we didn't have a slender element. But we do. But again, we have a stiffened element within it in one direction. So QS equals 1. So all we have to do is find QA. Now, if you look back in this section, again, everything that I have written down is from this section. 60.1-43. And we talk about this. We need to find this equation for B effective, where F, because we have everything in this equation except for that F. F equals Pn over AE. But in the note, it says instead of finding this, because these are unknowns, F may be taken equal to Fy, which we have. We know that's 46. So boom, we're going to do this. And it's slightly conservative. So not that we want everything to be super conservative in engineering, but that helps us out a little bit. If we needed to come back and sharpen the pencil later because we really need to push to the design to get it to work out, that this is a location we can come and try to make things work differently. But for right now, we'll just assume, or we'll be able to take F equals Fy. Plug everything in for this BE equation, and it needs to be less than or equal to B. Plug everything in, so T is your thickness of your member. B over T was in the section property. E you have, F is just Fy, so plug that all in. That gets you 4.784 inches is less than B, and now B needs to be taken not just base width, which is 8 inches. It actually needs to be defined as B minus your radii. And what this actually just breaks down to is B minus 3T. And there's more literature on this in the book and in that section that I suggest reading, but for now, it's just that. So that's this dimension here, which comes out to 7.65 inches, which is greater than your BE. So you know you're good, because that's B. So that's satisfied. So we're okay there. Your total area loss is equal to, so just the area of your section minus your difference here, which comes out to this. And then AE, your effective area, is 2.7. So this is your gross area minus your total area loss that we just calculated above. So that gets you your effective area now. And that's in inches squared. And now QA is just equal to AE, area effective, over area gross. And that gets you that. And again, units will cancel here, so make sure you're tracking those units. And what this effectively is, because now your QS you know is just 1, so Q equals QA times QS, which just equals that. That is your reduction in strength based on local buckling instead of flexural buckling. So we'll take that, and now we need to compute our local buckling strength. And again, we just pop back. If we go back here, you can go back to the beginning of chapter E7, section E7, and now you just have to run through here. And really you'll see, so we need to find FCR, your critical stress, and FE, your elastic buckling stress, because that's part of the F critical equation. And it's the same as local buckling, or as flexural buckling equations, just there's a Q inserted into the equation. And that Q is just a factor, and it's less than 1, so it's just a reduction in strength. So you'll run all these again, and I'm going to show you here just so we can keep following along. Compute this with Q, gets you 136. KL over R, we already know is 105.3 from previous. That's less than 136, so that's good. So we need to use equation E7.-2. So E7-2, so you get to use this one. It has an FE in it, so we need to go find FE, which we already know. That's at the beginning of the chapter. We've already solved for FE, so we can plug everything into this equation. Plug everything in, gets us 19.76 KSI, it's a stress. And now phi PN equals phi FCR, area gross. It's not area effective, it's area gross, remember that. Plug all that in, gets you 48 kips for local buckling, for compressive strength. And that's an LRFD, because we used phi. And so if I go back, when we checked flexural buckling strength was 53 kips, FB. So local buckling, now we only have 48 kips. So this controls. So that is the compressive strength of our steel HSS column. All right, that's it. Thanks everyone. I know this one was a little bit longer. 2 videos here, so you might see that messy splice in the middle there. I apologize, I'm still learning this. But yeah, until next time, please like and subscribe and let me know your thoughts and comments and where I can improve upon next time. Until next time, see ya.